Next speaker is Khim from Yonsei University.
Hello, I'm Khim from Yonsei University. Today I talk about how subdocument subhalos evolve in Redshift 1 clusters through galaxy-galaxy lensing. Let me start with some motivation why study subhalos. Subhalos have undergone tighter stripping, reshaping internal density profile. And by tracing radial trends and redshift evolutions, we can improve our understanding about dark matter properties. In this study, we focus on Redshift 1 clusters because Redshift 1 clusters are actively assembling and satellite galaxies are still unfolding. That means satellites are experiencing stronger tidal fields. By comparing it with rosy results, we can understand dark matter subhalos evolutions. So we first attempt to prove subhalos in Redshift 1 clusters. Then, how do we prove it? The invisible dark matter subhalo, we used galaxy-galaxy lensing. The tiny coherent distortions of background galaxies caused by some subhalos like this, we can observe shears and obtain the delta sigma excess surface mass density. Through this, we can characterize the subhalo structures such as subhalo mass and truncated radius. Actually, it is really hard to use in cluster environments because the clusters are made of a lot of mass components. But let me introduce these models briefly. Look at this subhalo in blue and background source in pink. We aim to quantify the amount of distortions of background galaxies. So of course, we should consider the subhalo mass itself's effects on the signal. So it shows this kind of shape in galaxy-galaxy lensing signal. And then we investigate the cluster environment, so we must consider a huge and massive host halos like this. This also affects on very large scales near 1 commuting megaparsecs, so like this. Yeah, some of these two terms is a classic approach. So we want to validate this model is well following or not. So we generate 300 mock galaxy clusters like this, and we stacked all subhalo signals like this. So here is the mock signals of subhalos. It is galaxy signals, radius, and the delta sigma. And under the truth value of the mass of host halo and subhalo and distributions, and this is the classical approach of galaxy-galaxy lensing in clusters. So as you can see, there is some gap in near 1 megaparsec. And so we thought, there is something, we are missing something. So what's missing in this environment? Yes, there are a lot of other subhalos like this here and here. So we cannot neglect this kind of a lot of other subhalos effects on the large scales. So it shows this kind of shape in our galaxy-galaxy lensing signal. We expect the sum of these subhalo and host halos and other subhalos can fully explain the galaxy-galaxy lensing signals. Like this. Let's check it again. Using mock galaxy clusters and stacking, and this is the signal of mock signal. And under the truth value, our model shows like this. Amazingly, our models will trace the most signals like this, so we can say we can recover the full signals. Then, what can we reveal through galaxy-galaxy lensing? There are 4 things: subhalo mass and host mass and truncation factors, and last off-centering dispersions. Actually, we don't know the exact center of the cluster. Because of that, we use some off-centering dispersions in our models to explain this kind of offset here. Yeah, this is the last slide of our methodology. Then let's move on our observational data and apply our model to real data. We used 28 galaxy clusters with HST data. It is provided by Khim et al. In prep. And the average mass from weak lensing is about 0.2 times 10^14 solar mass, and the mean ratio is about 1.11. And this one shows HST color image with weak lensing maximum contouring wide. And we select lens galaxies on red sequence through linear regressions. And we also select the background galaxies marked in green points like this under the red sequence. And on the right, we try to select the photometric member, which is cyan, within our 200 of host halo. And then, as you can see, the photometric member is well traced with weak lensing maximum like this way and this way. Following this process, for all galaxy clusters, so we've got about 4 million lens background galaxy pairs. Then we stacked all these signals. This is the results of our galaxy lens signals from subhalos. We can also find some significant dip in here. So we also test the truncated NFW profile and NFW profile for subhalo mass distribution. And we assume the host halo follow NFW profile, and also we assume the mass concentration from ASIAA et al. 2021 for subhalo and host halo. We fit it by MCMC, and this is the result. As you can see, both cases are well following with our observational data for across all radius. Then we also try to compare truncated NFW profile with NFW profile. This is MCMC counterplots for each cases. The axis is subhalo mass, host halo mass, and truncation factor, and sigma off-centering. Here is M sub and host halo mass and sigma offset. And we also calculated for NFW profiles subhalo, the mass within are truncated. As you can see, there is a big gap between truncated NFW profile and NFW profile in mass of subhalo mass and cluster mass. It is because without no truncations, this NFW subhalo extend to large radii. That means host halo might be stolen their mass by subhalo. Now, another key point in here, no matter what subhalo profile, as you can see, sigma offset is well constrained. So we decide to adopt truncated NFW profile for subhalos. This because it fits very well, like this solid line, and also it is physically reasonable. So to study subhalos in more detail and break degeneracies between truncated vectors and subhalo mass, we fix host halo mass and truncation and sigma off-center. Yes. The next step is we analyze our samples in more details and divide our sample by the distance from cluster center. The innermost regions are 1, and in middle are 2, and the outermost in blue is R3. And as you can see, all of cases, our models well trace the observational data. Let's zoom on the mass of subhalo. There is some weird features in like this. The subhalo mass according to the cluster centric distance, there is V-shaped feature like this. In R3, the subhalo mass is high, and at R2 it shows the lowest value, and again R1 increased, the mass is increased. However, in luminosity and effective half-light ratio radius shows not that significant change. So we can summarize like this. At R3, the subhalos experienced minimal stripping. At R2, they lost a lot of mass, and if they reach to the center of the cluster, the only massive subhalos can be survived. And we also try to find this kind of significant trend in low Z cases. Look at this plot. I also plotted the low Z cases. As you can see, in low Z, the result shows just monotonic descent like this. So we can interpret this difference as the time evolutions. And also we redivided our sample by luminosity, as shown in top left figure. And this is the results of the signals, and as you can see, our models well traced again our data. And we also compared roll and shaped results, like represented in blue and yellow, and here and here. The x-axis is luminosity, and y-axis is subhalo mass and mass to light ratio. As you can see, at the brightest end, there is some huge mass growth. It means as time goes on, mass growth concentrated at the bright end. Okay, this is summary. We present the first galaxy localizing analysis of 28 galaxy clusters at rest 1. We refine cluster galaxy localizing modeling by including other subhalo terms and off-center. And then we estimated truncated NFW subhalo mass and the truncation factor. And then we also investigate the mass trend with radar and luminosity. It shows redshift evolutions of dark matter subhalos. Thank you for listening.
Maybe one quick question.
Can you go back a few slides where you show the subhalo mass? So for the high Z results, you were implying that the innermost fin is kind of like a selection effect because you cannot detect the tidally disrupted subhalos.
Yeah.
So then, if I compare the outermost and the innermost fin, that means for those that survive, they don't get disruption at all.
Mm-hmm.
Does that make sense?
I think it takes some time to experience tidal strippings, and some simulations also reported their subhalo lose the mass. This is the outermost part, so they still hold their mass yet, and after falling, they lose their mass gradually, I think. and I think we need to compare this result with simulation data. We can more improve our understanding for these chiral strippings for some dark matter, in terms of dark matter properties, I think.
Well, if you have any other question, please ask over Slack. Let's